Welcome to our electric vehicle project. My team consists of Damien, Huzaifa, and myself, Abdul Rahman. Although our roles sometimes overlap, we set clear responsibilities. I led the mechanical assembly and soldering of the motors, while Damien developed the receiver and transmitter code, and Huzaifa collected data on equipment and documented progress. I later assisted with coding and fault finding on the hardware. The goal for this EV project is to make a small tank. Equipment used. We were provided with an EV chassis kit, 4 Kitroneck TT motors, 1 Kitroneck robotics board, and 2 BBC microbit version 2 units. The TT motors are compact and easy to integrate, making them suitable for a small EV platform. Limitation is the fragile copper terminal. Solid core wire can stress the terminal and cause failure. When correctly soldered and strain relieved, the motors perform reliable for basic motion tasks. The robotics board provides terminal blocks for motor connections, a power input block, red positive, black negative, a link header for the ultrasonic sensor and other components, an edge connector for the microbit, a power LED, and I2C adjustment pads. It contains dual H-bridge drivers that allow control of motor speed and direction. Advantages: compact size and the correct number of channels for 4 motors. There's also a current surge protection mechanism to protect the robotics board and microbit. Limitations: however, due to this, the board does shut off if it's faulty or the motors spike in current when turning on. Another limitation is that it dissipates some power as heat, reducing torque and battery efficiency. Security considerations: microbit radio communication is unencrypted, so messages can be intercepted or spoofed. In production, EVs, secure channels and authentication are essential to prevent malicious interference with critical functions such as steering or braking. This is very important in the military industry as they need to prevent cyber attacks on their equipment such as an electric tank or drones. Method: we began with chassis assembly while the coding was developed in parallel. I soldered the motor wires to the motor terminal. During assembly, one terminal snapped due to the solid core wire creating excessive strain. We resoldered the joints and used heat shrinking tubes to support the wire. All 4 motors were tested. They all worked but showed differing current pulls due to the resistance of the solder joints. Robotics board current surge fix. When the motor started from stall, the sudden current surge triggered the robotics board protection and caused the outputs to shut down. To mitigate this, we fitted a 1 millifarad capacitor across the supply to absorb transient spikes. This stabilized supply voltage during motor startup and prevented unwanted shutdowns. We implemented a handheld controller using a microbit as transmitter and a second microbit as receiver. The transmitter reads the accelerometer and sends single-letter commands by radio: F for forward, B for backwards, L for left, R for right, and S for stop. The controller displays an arrow for user feedback and transmits at a short controlled rate to avoid flooding the receiver. An ultrasonic sensor on the front provides obstacle detection. We created a dedicated subroutine that reduces the motor speed to 0 instead of turning it off. We use the selection statements to validate the distance when the move forward command is sent from the transmitter. We use the selection statements to validate the distance when the move forward command is sent from the transmitter. The vehicle stops 15 centimeters before an obstacle, giving it time to brake. The receiver handles 3 subsystems: radio reception, motor PWM generation via the PCA9685 motor driver, and ultrasonic distance measurements. The PCA9685 is initialized over I2C and provides stable PWM outputs for 4 motors. The receiver maps radio commands to high-level functions: move forward, move backwards, turn left, turn right, and stop motors. Each function writes the appropriate PWM values to the driver. We tested the motors after soldering and observed that the power output varied around 1.9 watts due to fluctuations in current. This was caused by small differences in resistance from solder joints. On the oscilloscope, the PWM appeared as a square wave switching between high and low voltage from the waveform. I measured a time period of 2.55 milliseconds, giving a frequency of approximately 392 Hz. This frequency is high enough to ensure smooth motor operation without visible pulsing and overheating the motors. We also tested the ultrasonic sensor by measuring its output at 2 different distances using an oscilloscope. The sensor showed minor deviation, but is acceptable for our EV tank. At 15 centimeters, the absolute error was 0.251 centimeters, percentage error of 1.67%, giving 98.3% accuracy. At 20 centimeters, the absolute error was 0.323 centimeters, a 1.61 error or 98.39 accuracy. These results demonstrate that the ultrasonic sensor is highly accurate for our system and is suitable for reliable obstacle detection. First, we aim to replace the current TT motors with a more viable all-terrain solution. Based on our research, the most suitable drop-in upgrade for the TT motors would be M20 metal gear motors, which offer a higher torque, better durability, and compatibility with the board's H bridges. These will support improved road wheels and tracks for the rough terrain. Second, we plan to add 3 additional ultrasonic sensors to achieve full 360-degree collision. Third, we will implement a servo-controlled rotating turret head operated by a separate microbit transmitter on a different radio group to avoid interference. Lastly, we aim to develop a GPS-based return-to-base failsafe, allowing the vehicle to autonomously return when the signal is lost. To show our planning for this next phase, we include both individual and group SWOT analysis and a detailed future Gantt chart. These highlight our strengths and areas for improvement, opportunities for expansion, and potential risks such as hardware failure and time pressure. A personal weakness and a group weakness is the lack of knowledge we had. A strength we had is we all learned quickly. However, due to the threat of illnesses, whether that's myself or others in our team, caused delays in accomplishing tasks within the time frame. In context, the importance of electrical vehicles is increasing rapidly, with governments investing heavily in net zero technology. Globally, there has been a clear shift from oil and gas powered transport towards electric propulsion. However, challenges such as battery energy density limitations and slow charging capabilities have slowed the transition. In addition, the security of autonomous and semi-autonomous systems, including military platforms like our EV tank, is becoming critical. Malicious users could potentially corrupt or override a vehicle's instruction set, creating serious safety and ethical risks. The issue is particularly relevant in the defense sector, especially with the ongoing conflicts such as the Russo-Ukrainian war. Small rotary and reconnaissance drones used by both sides are powered by electric motors and lithium-ion batteries. Because battery energy density still limits endurance, larger systems such as strike drones continue to rely on combustion engines. For example, the Iranian-designed Shahed series that was widely used currently by Russia and during the 2025 12-day war between Iran and Israel. Electrified propulsion offers several advantages for armored vehicles. Silent and stealthy movement. Battery power allows low noise, low heat operation, improving reconnaissance and ambush capabilities. High electrical power availability. Modern sensors, targeting systems, and communications require stable power supplies. Improved agility. Electric motors provide an instant torque for rapid maneuvering. Reduced fuel consumption in hybrid systems, enabling alternative energy sources and portable charging solutions that ease battlefield logistics. Electric propulsion reduces tailpipe emissions, which is essential for meeting global carbon reduction targets. However, there are also significant drawbacks. Battery weight and energy density. To store more energy, batteries must get heavier and larger, which reduces performance. Difficulties with recharging. In contested environments, vulnerability of battery packs to damage, thermal runaway, and fire. Vulnerability of battery packs to damage. Defense companies are currently favoring hybrid platforms. Examples include General Dynamics Abrams X, while Rolls-Royce and other firms are developing advanced hybrid power pack for future armored vehicles. So that concludes my work for this project. I've shown what we've achieved, what challenges we face, and what steps I'll be taking next to develop the EV tank further. Thank you for watching.